welcome back to our fourth session of the day. So today we have with us Ayo and Luke. Now, Ayo is an associate consultant at Advancing Analytics, where he has gained extensive experience working on both data science and data engineering projects. Previously, he worked as a land surveyor right after his degree before moving to the United Kingdom. His commitment and hard work enabled him to be able to switch careers and succeed in the world of data. We also have Luke with us, who's an AI consultant at Advancing Analytics and has been in the field for over 6 years. He transitioned into AI after completing a PhD in computational material modeling for applications in nuclear fusion. He has always taken an interest in using the language of mathematics combined with computing power to deliver tangible solutions to the world around him. They will be talking to us about leveraging Databricks for advanced geospatial analysis. Over to you.
Hello, can everyone hear me? Good. Hi, so yeah, thanks for that. I'm Luke, the cheery-looking person in the photo, and I'm joined here by my colleague Ayo, and going to talk to you all about geospatial data in Databricks. So I'm hoping that quite a few people here have used Databricks. Hands up if you've used it before. Good, that saves a lot of explaining. Okay, so let's kick off. So I hear it's good practice to have a contents page, so that's my contents page. So we're going to go through some terminology first, and then we're going to go through a nice load of problems for you that you can think about, and then also followed by a load of solutions to those problems, and then we're going to go through something called Mosaic, and then we'll round off with sort of a nice conclusion. So anyway, without further ado, I will leave you in the capable hands of Ayo to go through some terminology.
Thank you, Luke. Can everybody hear me all right? Yeah, thank you. So I'm going to begin with terminologies before we go into spatial data. Yeah. So to begin this talk, I would like to give some terminologies about these are some of the terminologies we use in geospatial analysis. First off, I'll start with talking about what geospatial data is. So geospatial data sets are just geographical information that kind of describes geographic locations. So every location on the Earth's surface can be described as with geographic data. Geographic data is used in various fields, agriculture, transportation, and various fields like that. Even as you are seated here, your position itself is a geographic data set. And these data sets can bring in various informations. They are so rich, and they are underlooked a lot. So this is the point where Geographic Information System comes in. So Geographic Information System is just the system that is designed to capture, manage, and store, analyze, and visualize the outputs so that you can take the insights you need from it. We have so many importance of geographical analysis, but the major one is that it allows us to solve complex location-oriented problems, I mean. Things like you looking for the best route from your house to a store. That's kind of a spatial analytical problem that has been solved by GIS. So we have various platforms for carrying out this analysis. I've pointed out a few of these. We have ESRI ArcGIS, we have QGIS, and Databricks. I know we could have used some other ones. So to continue this talk, I'll talk about the two types of data sets we have in Geographic Information System. We have vector data sets and raster data sets. So vector data sets it's about the points, lines, and polygons that are used to describe geometry in real-world entities. And we have raster data sets, which are the grids and tiles. They are arranged in a wall-to-wall pattern to represent regions. I know most of us are used to using Google Maps, so we would have seen some of these being shown there. Lines can be used to represent roads, for instance. Polygons can be used to represent buildings. Yeah, these are used on maps. So I was going to talking about some of these problems, some of the problems GIS professionals face with the platforms they use. So there's cost implications. Some of these platforms are not scalable. The processing speeds of some of these platforms are not good enough. We also have the storage capacity problem. Some of these platforms do not allow so many programming capabilities. And you can have, some of them are not a one-in-one solution, all-in-one, I mean. So talking about cost, if I use ArcGIS as an example, you have to pay for license for every time you want to use that particular software for GIS. And you renew every year, which can be expensive when you have a lot of employees or a lot of people who are to use this particular platform. Some of these platforms also do not scale very well when you are using large data sets. These platforms can be slow, and some of them depend on the computational capability of your system itself. So this sometimes draws the speed. It reduces the speed a little bit. Most of the times with Geographic Information System, we would need a very large storage capacity. And with some of these platforms, they rely basically on the memory of our laptops, or laptops we use. And most of the laptops we have probably about 2 terabytes at most, or more. And I remember working on a project back when I was in Nigeria. It was a mapping project where to capture images of the Earth's surface of an area, we're using drones. After capturing, we spent weeks on this particular project. After capturing most of these images, the size of the image that we're able to capture were a bit over 1 terabyte, I mean. And the memory of our laptop was lower than that, so we had to look for external drive just to save this kind of memory. So imagine having projects, a lot of projects like that. Where do you store this data? So another problem that you face is programming capabilities. Some of these platforms do not allow more than one programming language. You can maybe write just Python on one of them. There are some you can't even write SQL to query your data sets. And these are drawbacks with most of all these platforms. When it comes to all-in-one solution, some of these platforms do not allow many data professionals to collaborate on one platform. You can't have a data engineer, a data science, or machine learning engineer working in the same platform. So this draws drawback with the team. So I will be talking about the solutions to this later in the talk. But before we get there, I would also like to discuss about some problems that comes with classic GIS. If you look at this map, for example, that's Greenland at the very top and Africa down there. You would see that they almost look comparable. Greenland is a country and is almost comparable with Africa. But in actual terms, Africa is 14 times larger than Greenland. So this is a Mercator projection. And this will be one of the problems I'll be talking about. So Mercator projection was used back in the days, and it secures angles rather than, it doesn't show the area. So there's distortion with the area, and it secures the angle. So it's basically used by sailors then, because it's easier for them to move about on water using compass. So they can easily move from one point to another using this map. But when it comes to looking at the area, it does not show the area as it should be. So this is another map, and this is how Greenland should look like if you are considering the size and area of the map. But even looking at this is a Gauss-Peters projection, which is different from the Mercator projection I showed earlier. This one preserves the size, the area, sorry. This preserves the area and shows you how big Africa is compared to Greenland, but the angle is distorted. So it can often be used by sailors, and this is just to show the size. So this is how Mercator projection is being formed. This Earth, as we know it, we would say it's spherical, but in reality, it's not really a perfect sphere. The shape is even called a geoid. That's what it is called, and it's not a perfect sphere. So we try to map out, project what the Earth, the continents and the map look like from a sphere to a 2D map. So projecting this in Mercator projection, they used a globe. Imagine a light from inside the globe. I don't know if many of us have seen such globes. I remember when I was in uni, we used that in one of the projects. It was used as an example in school then. We have this globe with the continents all over it, and it has a bulb inside. You switch it on and wrap paper around it. So it kind of projects the continents on the paper. But the issue with it is that as you go towards the poles, it kind of gets distorted. It exaggerates the size of the image. But this is how Mercator projection was formed, the 2D maps. And we have so many other projections, but the issue with all of them is that they are all distorted at some point. I would like to talk about the coordinate reference system. So every place on Earth can be specified by a set of numbers called coordinates. We have two kinds of reference systems. We have the geographic coordinate systems and the projected coordinate system. The geographic coordinate system uses the longitude and latitudes, which are angles. Yeah, we can see the shape. The longitude goes vertically and the latitude goes this way. But these are from using the Earth as a sphere. But when the Earth gets projected, like we have the conic projection, cylindrical, and the plane, when the Earth gets projected into a two-plane map, we can no longer use angles anymore, and that brought about the projected coordinate system. So the 2D map is formed into grids, which gives us the X and Y axis, and that's how we got the easting and northings we use, basically. So one other thing is, because of the Earth is not a perfect square, it's very hard to find the center of the Earth. And most of these coordinate systems are being referenced to the center of the Earth. So we have so many datums. It brought about so many datums that are calculated mathematically. We have assumed calculation of the ellipsoid of the Earth. So this was a practical that was carried out by the European Petroleum Survey Group. They took the measurement of Netherlands, that's the map of Netherlands, as we can see there, and referenced it from different datums. As we can see, they appear in different positions. I remember back then too, when I was in Nigeria on a particular site project, I referenced, we did a research just to see the difference in distance from using two different datums. So I used, in Nigeria, we use Mina datum, for instance. And we have the World Geodetic System, which is WDS84, which is referenced to get your coordinates also. So I wanted to see the difference between the WDS84 coordinates of the same points and the Mina datum. And after acquiring the coordinates, I realized that it was you always have about 100 to 150 meter difference. So that's why Netherlands looks like this, and it's not in the same position when compared to different datums. And datum is just, in a layman English, is just like the center of the Earth. So all coordinates have been referenced to the center of the Earth. One other problem I would like to talk about too is it concerns the relational database management system. The relational database management system makes use of indexing to store its data. So for instance, if you look at that image, I have two major continents, the R1 and R2. Then I have subcontinents in there. R3, R4, R5, R6, and R7. So if I have a data set in here at R13, to query the data set, RDBMS makes use of indexing for faster querying. It begins to search for where the data is from, if it's in R1 or R2. If it's not in R2, it goes down to check if it's R3, R4, R5, then later finds it in R5, R13. So the index is more like R1, R5, R13, and it stores data sets like that. But the issue with the RDBMS is that it doesn't scale when it comes to big queries. And when using joins, for instance, so these are two RDD data frames in the RDBMS. It kind of shuffles this RDD when you want to join and make sure they look the same and have unique IDs. So it's easier for it to join. But when it comes to using joining your RDD with a vector, because vectors have unique IDs of their own, it becomes harder for it to join. So it cannot join. So that's why we have to shift from using the tree-based index system to grid system. But my colleague will come in now and talk more about that and give a solution to most of the problem I've mentioned.
Thank you. Right, so yeah, we've run through a whole host of issues when dealing with geospatial data. So I'm going to get round to talking about some of the solutions you can use with Databricks and other methods. So firstly, as I have shown with vector data, you have a lot of issues with scaling and things like that. So if we turn to something like a grid-based system, it makes life a lot easier. So normally how they work is you'll have, say, an index, and then if you imagine that single integer there, you see in the diagram, then the second integer comes, and then the third, and each one represents traversing down to a more of a resolution. So there's a number of different grid systems that you can use, but I want to talk to you about one called the H3 index. I'm not sure if anyone's heard of it here, but it's, as you would imagine, it's involving hexagons. Strangely enough, it was created by Uber. They were having problems with like picking up customers and density, so they came up with the H3 index. It's written in C, so it's nice and fast. It's got about 16 resolutions, so it can go really high, or it can go to about 1 square meter, which is roughly like a person looking down on them. So yeah, it's a really great tool. I'm going to talk a little bit more about it. Yes, as I said, it's created by Uber, but if you're like me, you're probably wondering, why is it a hexagon? I mean, it seems like a bit of an odd shape, doesn't it? So you'd understand if you had circles, because circles don't really tessellate, but why not a triangle or a square? Why have they picked hexagons? So I'm going to explain to you why and try and convince you of why a hexagon is a good idea to use as a tiling system. So the first thing I want to talk about is neighbourhood traversal. So when you're calculating neighbouring tiles, there's some values that you need. Now, let's compare triangles and squares. So you can see there on the diagram that you need quite a few distances for triangles. You need 3. A square takes 2, but actually with a hexagon, you only need a single distance, and you can replicate that value as you go along the neighbouring tiles. So it's unique in that sense, and that's one of the reasons, but there are other reasons. The other thing I want to talk about is subdivision. So if you see here, you can see that a hexagon, it subdivides, and this is important with a tiling system because you need to delve down into tighter resolutions. But if you notice, it doesn't quite subdivide perfectly. You kind of had to twist it slightly to get it in, so it almost subdivides perfectly. However, squares do subdivide perfectly. So why have they not used squares? They could use squares to do this. So there is another reason, and this is sort of the final reason, but it's one of the most important, and it's more of a superficial reason, but I'm going to explain it. So we talked about distortions and things with projections. So these are typical projections, but I want to talk to you about something called a Dymaxion projection. So these are the normal ones that you see, like a genomic projection. However, this is a Dymaxion projection. So if you see, it's flattened out, and I'm going to explain what it actually is in a bit, because it looks a bit confusing from that, and it will come clear exactly what it is in a minute. So, I don't know if anyone's into like Dungeons and Dragons or role-playing games, but imagine those dices with all the sides on. It's basically that, but unfolded. Another trick that they've done, if you notice, all the splits, they're around the ocean. They're not on the land, so they preserve the splits for the ocean so that you get less distortions on the land, because really it's the land that you're interested in. They also don't suffer from the same level of distortion. So I was talking about Mercator projections. As you get closer to the poles, the distortions get larger. Because it's done in such a way, you don't get that same level of distortion, so it's a very useful way to do things. I mention all that to say this. So if you use that projection with different tiling systems, let's have a look at this. So this is Google's S2, so that's, believe it or not, that's actually a square. So this is actually in San Francisco. And going back to our example of Amsterdam, if you look here, the square turns from a diamond to a square, whereas the hexagon, it actually preserves its shape a lot better. It's more or less a hexagon still. So in terms of the values, it doesn't really change much in terms of the calculations. However, visually, it just looks much nicer than using the S2 grid system. So that's mainly why they used it, and I hope that's sort of given you an idea of the H3 index. One last thing before I talk about something else. I gave the game away a bit there, but can anyone notice anything about the grid system here? Give you a few seconds. All right. Okay, I'll just say it. If you look here, you might notice there's a few pentagons there, and that is not a mistake. Can anyone guess why there are pentagons amongst a whole load of hexagons? Okay. Sort of, yeah. It's actually to do with, if we go back to this when it's rolled out, it's to do with these bits here, because if you imagine, if this has to fold up to represent a sphere, then you have to almost cut a chunk away at those certain points to make it curve inwards, and that's why there are some pentagons thrown about in there. Like I said, it's not a mistake. So we're going to talk a little bit more about Databricks now. So Databricks, we're going to talk about something called Mosaic, not to be confused with the GenAI Mosaic. This is actually a geospatial library, and it uses the H3 index as well as some other tricks. So I just want to talk a little bit about classic GIS. So with like online transaction processing databases, these were typically used for using geospatial analysis. So the storage was quite close to the compute. They do have quite good things like low latency and stuff, but in terms of scaling, it can get quite expensive. Now, Databricks has got some very good techniques or tools that you can use to help with this. So, can anyone think of anything in Databricks that can help with things like storage and compute for GIS? Tell you what, I'll give you a clue. Anyone guess? It's Lakehouse. Yes, the Lakehouse. So the Lakehouse is very good for this, and I'm not sure if anyone's familiar with things like Z ordering, but if you imagine like a tiling system with an index, Z ordering helps because, just to briefly explain it, so if you have like a delta table in Databricks, it's basically Parquet with bit of metadata thrown on top, but it utilizes things like data skipping and stuff, so you can effectively query from those multiple files fast and efficiently using Z ordering. So it's a bit like indexing in SQL. So if you imagine using that, it makes things a lot easier. The other thing I want to talk about is something called the tessellation technique. So the tessellation technique, there's a few ways of doing these operations. So classically, that's the one on the left is how you do it traditionally. But then with grid systems, you can do tessellation. And then you can also do something in between, which is like a discretization. So it's sort of like it's a compromise if you wanted to. But the tessellation technique, I want to explain a little bit more. So how does it work? So let's take this polygon, for example. So obviously, it's discretized with the grid system. But let's say you want to work out, let's say, if a point lies within this. So if you notice, the majority of the grids, the tiles, I mean, they're red, as in the majority of the tiles are going to be whole tiles, so complete tiles. There's only some on the outside that are actually going to have some sort of polygon or shape going through them. So if you look here at that point there, you notice that it lies along the boundaries. So what you can do is you can first align that the index with the index of the point, when we were talking about the H3 index, and then followed by that, you can then do the operation to check whether the point actually lies inside the polygon. Now that might seem weird that I'm going into this, but I'll explain why that is significant in a bit. But let's take the easier example. Let's say that it's a whole tile, so it's a core tile, so there's no lines going through it or anything. It's very easy to work out if that point lies within that shape, because you just match up the H3 index, and then there you go. So I'll explain a little bit later why I've gone into that. But very quickly, let's quickly run through some use cases. So this is a company called Fasos, and they used Mosaic with the H3 index, and they got quite a bit of performance, so 2.5 to 10 times better performance. I really like the one at the bottom though. So they utilized Z ordering in Databricks, and then it reduced from 2 hours to 7 minutes, which is amazing. I think that's a huge amount of speed up. They also, you can also, I haven't put it here, but you can also use this with Photon as well, if anyone knows what that is. So we've got about 5 minutes. I'm hoping I can just very quickly go through a demo of what it looks like, and then hopefully some time for questions as well. Let's hope that the demo gods are smiling on me. Right, so yeah, apologies, I haven't had a huge amount of time to explain Databricks, but it sounds like you're all quite familiar with it, which is good. So getting used to getting Mosaic to work. So if you're used to ML runtimes, they normally have the libraries already packaged up for you, but you actually have to install it. So this is what it's called, Databricks Mosaic. So if you just install it quickly, the second bit to get it to work is you have to enable it. So you have to enable it with those few lines of code, but once you've done that, you can get using it. So the example I'm going to talk about is using polygon data. So these are basically, we're going to use an example of New York, and anyone that's used Databricks has probably come across the New York taxi data set in Databricks. So we're going to focus on New York. So these are polygons of different crime precincts. So what we're going to do is we're going to look at the taxi activity that happens within these polygons. So you want to find the density of taxi activity within these different polygons. So first off, I'm going to load it in, and let's see if I can shuffle to the side a bit because I just wanted to show you here. So this is what a Mosaic index looks like. So you have a few components. You have the actual ID, the index. You have the well-known binary, and then you also have, and this is the key bit, is core. So what that's referring to is whether it's a whole tile, and that will become relevant a bit later on when we try to do a join. So, right. So let's go down. So the good thing about Mosaic as well is it has a library called Kepler integrated into it for visualization. So if I zoom out a bit, you can see the polygons there. So that's New York, if you recognize it. I've not been there myself, but yeah. So this is basically to do with the taxi data. So I've just loaded it into basically a Hive table, but you don't have to worry about this bit. It's just sort of cleaning it up a bit and doing a bit of wrangling. But what I'm going to do is I'm going to pull out a sample of it. So a week's sample is what we're going to look at. But if you see there at the count, even a week, it's quite a lot of data. So you can see about 2 million rows. So a lot of taxi trips going on in New York. So the next bit is we're going to, you have in this data set, you have a pickup point and a drop-up point. So those are the longitude and latitude points. What I'm going to do is align them on top. So you want to look at the density. So where when someone gets picked up from a point and when someone gets dropped off at a point, that's two sort of activities from this one taxi. So if you put them together, so then you have two coordinates for each taxi trip. So the next step is if you want to work out the density. So what you do is you do a group by to get the density, and then looking at this, let's see if I can zoom out. Bear with me. So you can see here, this is you can see the H3 indexes there. So this is to do with density, and you can see here that the bright yellow is high in density, and as you go further out, it drops. So what we want to now do is work out what the density is between all these polygons. So the polygons are the crime precincts that you saw. So what you want to do is you want to do a join to see if those points lie within a particular polygon. Now this is where the core index comes in, because it's a trick that you can do with Mosaic to really speed things up. So you join on the index, so when the index matches the index of the point. And the first bit you want to look at is you join where you firstly join on all the core tiles, so the complete tiles. This operation is so much faster than doing the ST contains operation, which takes much longer. So if you get that out of the way and do all those first, because you know that if it matches the index and its core, then it definitely lies within inside that polygon. And then you leave the last bit of operations for non-core, so when there's like a line going through it or something, and then you can work out whether the point actually lies inside or outside that shape. So this is the reason that I was talking about the tessellation technique. It really helps speed things up. And once you do that, it might not look like much here, but give me 2 seconds to show you what it's done. It's actually done it here, but you have to do some fiddling about to see that it's actually done stuff with density. So very quickly, let's walk through it. So the fill color, let's change that to, oops. Bear with me, let me run this again. Okay, it might take a little too long, and I think we're a little bit short for time. So if it takes too long, I'll leave it. But I'm happy to answer questions about it later. But essentially, what you can do, I'll just explain it because it's probably quicker. Is you can visualize it, so you can make it show the color spectrum on the different polygons, so you can see them, and you can actually adjust the height to relevant to the density. So if you go down to the bottom there, let's see if it will work.
Let's switch it on.
Yeah. Okay. For some reason, it hasn't really pulled in the density. I'm not quite sure why, because this was working perfectly fine just before they did it. So I do apologize, but that's essentially how it works. Okay, so just to round off the presentation, let's go back to the last few things to talk about before leaving some time for questions. So, Databricks addresses cost. So you're not paying for an expensive library like ArcGIS. You're actually just paying for the compute. It scales very well because Databricks is very scalable. It has storage benefits, and Databricks is sort of it offers an all-in-one sort of solution. So I guess the main takeaways from this are dealing with geospatial data. It can be quite challenging. There's a lot of problems that come with it. But also projections, you have to bear in mind that there are distortions and you have to work around them. Joins are sometimes quite difficult with polygons and geospatial data. But Databricks, of course, has the answer with the H3 index and Mosaic. And also it offers a lot of benefits for geospatial analysis. Anyway, thank you. And anyone's got any questions? I think we've got about a minute left.
Yeah, thank you very much.
Yeah.
Yeah, I've just got one question in regards to the tessellation. Does Mosaic handle the pointed polygon bit once you have a point which is in, excuse me, in a tessellated cell?
As in, can it capture a polygon once?
Yeah. So in the example you showed there, the first bit you showed that you had a point in a polygon.
Yeah.
Which was inside the diagram because it was inside the polygon of the object, but it was in a split polygon. So in the tessellation side of it, do you have to put more focus onto how you find out at that point with the H3 cell?
Yeah, so there's further operations that you do. So like that SD_ contains, that's a separate operation to check which side it lies in. Yes. But yeah, if you do the quartiles first, then you leave the more expensive operations for the outside. Exactly, yeah.
Fantastic, fantastic double act. Thank you very much, both.
Thank you.
Lunch is now available outside, and we'll see you in 45 minutes for the next session. Thank you.